Good afternoon. We have more physics and art, or art and physics and mathematics. First speaker this afternoon is Roberto Zenit from the UNAM, and he'll be talking about hydrodynamic instability and artistic painting.
Okay, thank you. Good afternoon. It's really a pleasure to be here again. It's my first time at the Newton Institute, but I've been before to the University of Cambridge. And again, thank you to Andre, where is he? He's really, I'm listed as a co-organizer, but he's on all the heavy lifting, and I was just there for emotional support. So he is the man. So today I will tell you about this work that we've been doing in my group. And again, I put the question mark at the end because to me, before we started doing this work, I was completely unaware that this could be in the same title. So I hope that I am able to convince you that there is a direct connection. So, and again, what I will be speaking to you about is me as a fluid mechanicist. How can you use this set of tools to help art history in particular? So again, I have listed here art and fluid mechanics, but in particular I will talk about painting and fluid mechanics. Okay, so this is what I did. I did a search on Google, famous British paintings, and this was number 3, I think. And again, this is by Francis Bacon. It's a relatively modern piece, and again, it's a piece of art. And people like me who don't have any artistic training, we look at this and you say, well, this is trying to express something, and of course, it's conveyed to us through the use of a canvas and paint. And again, I found this particular painting particularly interesting. Okay. So, but again, the vision that I have from again being a fluid mechanicist to art and art appreciation is the following. Right? All paintings start like this. There's nothing, just a blank space, and then we have to add ingredients to actually produce something that has aesthetic value, right? And of course, the first thing is that you need is the materials, fluids, right? Then you need the maestro. Huh? And what came to me as a realization when I was starting to do this project is that, in fact, to achieve a piece of art, you need to combine these two, but this guy needs to know something. He knows fluid mechanics, and he knows fluid mechanics in a very deep, empirical way. Again, this is what we know from the people who do fluid mechanics. We know that, in order to achieve motion, you need to fight against viscosity, you need maybe apply some pressure gradient, and then gravity also plays a role, right? But the artists, what they do is they study fluid mechanics, but they do it in a laboratory sort of way. So they become masters of handling the paint to create a beautiful image, right? So this is my realization. Painting is fluid mechanical. And this is a little movie that one of my students made, trying to convey this idea. You have a fluid, you apply a certain shear stress, a shear force, and then you end up with a pattern that is placed on a canvas. And what is most interesting is that depending on the amount of shear, the amount of paint, a number of parameters, then you can achieve a static image like this. In industrial applications, what you want is that the paint to be spread thinly and uniformly, but in artistic painting, you look for the details. You look for things that are not exactly uniform, right? So again, you choose the brush, you choose the volume of paint, and then you choose the speed at which you apply this paint. And then you fight against the properties of the fluid, in this case viscosity, density, and surface tension, to achieve a texture that will be used to convey an aesthetic idea. Okay? So in this talk, I will tell you about 3 tales, 3 stories of things that I have learned from art history in which fluid mechanics has relevance. In all of them, but I will tell you about 3 ones in particular. And again, to me, this has come as an unexpected source of inspiration for my work in fluid mechanics. First, I will tell you about Siqueiros and his accidental painting technique. Then I will tell you about Jackson Pollock, which is very well known because of the fluid mechanics involved in his paintings, and I will talk about dripping. And lastly, I will tell you about a Mexican-Spanish painter who is not very well known from what I've discovered outside of Mexico, and she used a technique called decalcomania, and I will tell you about it and how it connects. How can I connect these three names in one presentation? This is Siqueiros. Siqueiros is a very well-known Mexican painter. In particular, he was a muralist and he was a political activist. He was hardcore left-wing party leader, and that's why he was in prison at some point in Mexico. And again, his paintings have become part of the modern Mexican culture. Here is a painting by Siqueiros, and it's called The New Democracy, and this is actually in a big wall in the Palacio de Bellas Artes, which is the Palace of Fine Arts in Mexico City. If you ever visited Mexico City, you probably visited this place, and it's an enormous, beautiful piece. And again, the subject matter that interested Siqueiros is always filled with social content, right? This is another mural, another famous mural by Siqueiros, which is actually part of my university, the National Autonomous University of Mexico. And again, it has this theme, this subject. It's the people to the university to the people. Our university is free and it's public, and it has this very social connotation to it. On the other side, there's Jackson Pollock, which is an American painter, and he's an abstract expressionist. Here's one of the famous photographs of Pollock working. And this is a typical Jackson Pollock painting. Again, entirely different subject matter, but it has this beauty to it that, Pollock became famous because of this dripping technique that I will tell you more about it. This is one painting, and this is the painting that it's nearest to you. This is at the Tate in London. This is called Summertime. There's a zoom of it, in which again you can see these lines of paint that are drawn on top of a horizontal canvas. I will tell you more about it a little later on in the talk. This is Remedios Varo. Again, this is a Spanish-born painter that left Spain as a result of the Civil War and found a home in Mexico. She's the subject matter of her paintings is mostly surrealistic. And again, this is a photograph of her painting, and this is one of her most famous paintings. It's called the Flute Player, and again, it's a surreal sort of image in which you have a fairy emerging from some kind of bush, and again, I'm just a regular guy. I'm not an art dealer, but I like this painting, like most people do. Just you find something about art that is you cannot put in words. It's just something that it's appealing to you. What is particular, and what I will discuss more later, are the type of textures that you can see in paintings like this. Here's another painting by Remedios Varo. This is called the Gypsy Caravan. And again, when you first see these paintings or any painting, you don't notice all the details that have learned to notice afterwards. So I will not touch upon it, but I will come back to it. Okay. So again, the question that I'm posing here is that there's three painters, and of course there's fluid mechanics. They know the Navier-Stokes equations better than us. And what is the common language between these, in particular, these particular three painters? So what I want to say is that they achieve texture to produce aesthetic images through hydrodynamic instabilities. And I will tell you what they are. Again, hydrodynamic instabilities are the core matter of many of us. We have an expert on this hydrodynamic instabilities right in the room. Again, flows at a certain point become unstable because they're unable to dampen perturbations. You know, these perturbations grow in time or space, and then you end up with a shape like this, classical Kelvin-Helmholtz instability. Okay, so again, I will show you examples of how I interpret the patterns of these three painters through the view of hydrodynamic instabilities. I will not go into any details. I am prepared to speak more in detail in another session maybe about any of these subjects, but I will just show you some ideas, some guiding ideas of these three problems in which we're working on. So I will first show you this technique, which is either called controlled accidents or accidental painting technique, and this is the technique that Siqueiros developed. Again, this is a painting by Siqueiros, which was painted in 1936, and it uses a very fluid kind of liquid. It's not a paste like a paint, and it's painted on plywood, and this actually lives in the same museum, the mathematical museum that was discussed earlier. And again, the subject matter is it's very interesting because of the view of Siqueiros, the view that Siqueiros had of the world, and particularly of Mexico. This is it's called collective suicide. So the subject is that, you know, you have these conquistadores, the Spanish troops advancing, about the Mexican culture, and instead of subjecting to the conquistadores, they prefer to commit collective suicide. This is not what happened in Mexico, of course. You know, there was a lot of mixing, but again, this is how the original culture was destroyed by this process, and the subject matter is interesting. What is most interesting is all the painting techniques that Siqueiros used to produce this piece. And again, there's a sea of swirls and many textures, and I have one zoom that is particularly interesting because of the following reason. I will show you a zoom of this region over here. Here it is. So this region was painted just with two colors. That's why I decided to focus on this one. But these type of patterns are repeated throughout the painting. Right? And this is how I started working in this subject. My friend Sandra Cetina, who is my co-author in all of these studies, she's our historian, our conservator at the School of Aesthetic Research at UNAM, and she came to my office with this. I said, how do you paint like that? What did Siqueiros do to paint a texture like this? And I was instantly hooked. It's like, I need to find out. Right? So what we did, and this is what we have tried to reply to repeat in the different subjects of painting analysis, is this. First, we need to find out what was the procedure that the artists follow to achieve these textures. In the case of Siqueiros, again, being now a part of Mexican culture, all of his letters are archived and they belong to the National Treasure. So we went and dig the letter that he wrote on that day in 1936. He was in New York and he was organizing an experimental painting technique. And he had this girlfriend in Mexico, so he wrote a letter to her and described what the painting that I just showed you. And here's a little translation. You know, of course, I translated it, so it's probably not the best translation. But again, he calls this a method of absorption. I will use the stick now. It's a method of absorption. When you superpose 2 or 3 colors, they infiltrate into each other. And that's all we have. We don't have any details how he did it or etc. But then and then he says that they produce the most magical fantasies and forms that the human mind can imagine. And then he goes on and it's very poetic. It's similar to the formation of Earth, and he basically explains everything out of this letter and this painting technique. So what we did then is we just took the fluid mechanics part. So what we do is we try to reproduce this in the laboratory, by basically pouring one a layer of paint into a horizontal surface. This is black paint. Then it spreads out a little bit, and then on top of it we pour white paint. Just again following the idea that Siqueiros had, and at the end we have something like this. It's just a pancake, a double-decker pancake. So what we did is that we actually determined the properties of the two paints. They're very viscous, and most importantly, they have different densities. So this is what we see when we pour this on top, one on top of each other. Here's more or less the center of where I'm pouring, so this part is destroyed, but at the edges you see the pattern formation, which is again the signature of the accidental painting technique. This texture that you see here is that in the paintings of Siqueiros of that period of time. Here's a zoom of the same thing. Let me try to stop here. Stop. Up. So again, so what you see is these patterns of black alternating black and white. And again, what did we do right to achieve this pattern? Well, we did many experiments, and these patterns appear only by changing the thickness, the types of paint, the surface tension. Actually, we changed the surface tension with surfactants and so on. And the texture would appear only when the top fluid was denser than the bottom fluid. So we have a hydrodynamic instability, which is widely studied in the fluid mechanics community. Rayleigh-Taylor instability, but it's very thin and it's very viscous. And again, when after the texture appears, then the paints begin to cure, and then you freeze the instability and you preserve it, and that's what you get like this. Okay? And again, what you see from these paintings is the emergence of the black paint being pushed upwards and the white paint being moved downwards, which in the literature of Rayleigh-Taylor instability they call that bubbles and plumes. Okay? So for Siqueiro, the key element was to abandon the way painters usually paint. Again, he used very fluids with very low viscosity, such that they could spread out. They placed the canvas horizontally, such that they could do this exercise like this. And again, what he was doing, he was studying Rayleigh-Taylor instability, and he didn't know about it. They said that sometimes they appear, sometimes they don't appear. It actually depends on the color combination. What they didn't know is that light colors, whitish colors, have titanium dioxide particles, which make them denser than, for instance, black, which has carbon black particles. So carbon black in a dilution is lighter than white, which has heavier particles. And again, I will not talk about this in this presentation. We actually did a linear theory and predicted the size of these patterns that match pretty well with those in the paintings of Siqueiros and in our experiments. And again, we have tried many other experiments, and we are actually able to work. Well, we, as in my students, are very skilled at changing the size of these recirculation cells, again, that match the predictions from linear instability. So what Siqueiros did is he learned about these instabilities, and he was very good at it. So he wanted instabilities to produce the patterns. Now, I'm going to change painting techniques, and I will tell you a little bit about the work that we've done with dripping, the way Pollock used to do it. And our dear host, Andre, has also worked in this subject. So if you have never seen pictures like this is how Pollock achieved his painting, his dripping technique. Again, placing the canvas horizontally, and again, also using fluid-like paint, very, not paste-like, but liquid-like. And he would take a bucket of paint and then insert either a brush or a stick and just very skillfully dripped the paint on top of the surface. And if you had, I found this on YouTube last night, right before I took my plane. The difference between Pollock and many other artists is that he loved to be photographed. So he allowed Hans Namuth to actually film him while he was working. And this is very rare. You know? He's one of the few artists that we have all these documents that we can use to interpret how he was painting. Here's one working on the side. And actually, this is a fascinating one. Hans Namuth convinced him to paint on top of glass, so we can actually see from below, and he was painting. This is a beautiful image, and we will actually use it to interpret what he's doing. Right here he is, you know, acting for the camera, and here he is. Huh? So you can see how he's dripping the paint to create these abstract images. So you have these long straight lines like this. Okay, so this again, these movies are they provide incredible amount of information for us to try to understand how he achieved these type of paintings. So he was again, during this particular movie, he's talking about the technique itself, how he is able to achieve these type of compositions through this dripping technique. I will not read this, but you can find it if you just Google Hans Namuth and Pollock. You find an incredible amount of information. So what is most interesting from the art history view of these two subjects is that these two guys knew each other. This is Siqueiros in 1936, and this is Jackson Pollock. Siqueiros was already a superstar in the modern art world at the time, and Pollock was just still aspiring artist in New York. So they both attended the same experimental painting workshop in New York in 1936, and that's why they both use very liquid-like paint to do their art, and also they use horizontal canvas. So the invention of painting horizontally comes from this experimental painting workshop in 1936. Okay, so what we did is again we want to know what are the range of physical parameters that one must know in order to paint like this. So what we did is we took this idea, this view of the Pollock painting technique, and we transformed it into a laboratory experiment. And this has also been done to study this subject. Again, we have a syringe that is injecting a certain amount of fluid and is being deposited on top of a substrate. And in that case, the hand is the syringe and is moving. Of course, in the laboratory frame of reference, it's better to fix the syringe and then just move the floor, but it's the same problem. So we conducted experiments. We used two paints that have similar properties than those used by Pollock. And again, we fixed certain parameters. We fixed the properties of the fluid. We fixed the diameter of the nozzle, and we fixed the flow rate through the nozzle. And we only varied the speed of the floor and the height from which the film is dropped on top of the surface. And these are the two dimensionless variables that I will use to show the results. It's just the dimensionless speed and dimensionless height. And this is how things look like. And again, this is for very slow moving floor and not very large height. So this is how you would do pastry. Right? The fluid reaches the surface, and if it were not moving, it would just coil itself. And this is a well-known hydrodynamic instability, which is called the coiling instability. There's a nice review paper here from 2012. And actually, John Lister has worked in this exact problem, what they call the fluid mechanics sewing machine. If you increase the speed of the floor just a little bit, you still get coiling, but you get a different length from coil and coil. If you increase the speed even further, you can actually be able to prevent coiling. No? You see that this thread is about to coil, but then the speed is sufficiently large to prevent this coiling. So again, in a very nice paper in Physics Today, Andre and collaborators, they basically explain what can you do to prevent curling. Is that the speed of the floor has to be larger than the rotational speed of the coil. And this is actually very well understood and depends on what parameters dominate. It can be gravitational or it can be inertial. And again, what we did is to draw all the experiments, all the experimental results in terms of the dimensionless speed as a function of the dimensionless height, and the red dots are the curling figures, and the blue symbols are straight lines that are deposited after you have done this experiment. And again, and this shows a white space here because again, now we know how to curl or not to curl. But what we want to know is if Pollock was intending to be curly or not to be curly. Okay, and just one very quick technical comment. You can actually show that for the gravitational regime, the threshold between the two is square with the distance, with stress square with the height, or square root with the height. Okay, so what we did is we took the videos from Hans Namuth, and we actually measured the speed at which Pollock was moving his hand, and here is the speed of the hand, and here's the height from which he had the hand on top of the horizontal canvas. And again, there's some uncertainty here, but if we assume that Pollock was some certain height, we can actually have these measurements, and the mean is over here and the standard deviation is over here. So with these two measurements, we can actually place Pollock's painting action on top of our laboratory results. And this is how it looks. Again, what we found is that, for at least for this particular painting in which he was painting through the glass, Pollock was over here. So all the lines that he produced were actually straight. They are not curled. They're a little bit curvy because of the design that Pollock is doing, but they're not fluid mechanical curly. They are artistic curly. Okay? So this is actually a nice result. And if you go back to see Pollock's paintings, you actually see what I just said. Not fine curls, but thick and long curls. So again, what we learned from Pollock is that he was the best fluid mechanician. He knew his paints. He knew how they're going to behave, and that's why when they interviewed him, he said that there's no accident. I know exactly what is going to happen. So, and that means that he knew about this curling. He knew about the ranges of viscosity that you need to have in order to prevent curling instability. That's why I said bad, because in all of his paintings, the action that he took and the paints that he used were such that he would prevent the instability from happening. Okay? Well, now, just to change to my last painter of the day, and I will tell you about this technique called decalcomania, which was used by Remedios Varo, but also used by Max Ernst and Oscar Dominguez and probably many others. But as opposed to what I have shown you for the two previous painters, there's actually very few documentation of how you paint like this. There's not a lot of discussion on how this is achieved. And I have chosen this particular painting of Remedios Varo because, well, the name is obvious, Catman, because of the following thing. As you can see immediately, this is a mirror image. So what was done is that this is the patterns that are produced with decalcomania. You see these striated patterns, these Venus-like patterns from this side to this side. Huh? And again, you see also this here and over here. As I said, we were unable to find a physical, at least not even physical, just a casual description of how this is achieved. And this is how this is achieved. My student actually made this video such that I could tell you about it today. So you have a piece of paper, and then you inject a little bit of paint, and then you place a flexible sheet of, in this case, paper. You spread it thin, and then you just rip it off like that. Okay? And what you produce is this. So painters that use decalcomania are looking for these textures. So what we did, again, same idea, we have some feeling of what the painters are doing, and then we reproduce it in a controlled manner in the laboratory. So what we have is two glass plates. They're transparent. We film from below, and we place a certain amount of fluid, of paint on top of this, and then we do like this. And we just open it up in a controlled manner. And this is in an angular way because it's easier to do in the laboratory. And this is what we produce. This circle over here is the paint, which is transparent lacquer, just to aid the visualization. And what you will see is that how this edge will progress in time as I am moving the top plate in time. So you will see the edge becomes unstable. You see these fingers forming, and you have decalcomania. And it's pretty. And this is another instability. It is a form of Saffman-Taylor instability. When you push a fluid, a viscous fluid with less viscous fluid, you get this unstable advancing front, which again is very well studied in fluid mechanics. And now we get to do some measurements, some quantification. Again, if I were an artist, what would I want? I would want to control the number of fingers. I want many fingers or little amount of fingers. And this is actually, in this very nice paper here, the number of ramifications is proportional to the capillary number and to the aspect ratio of the drop. And again, what we did with our experiment, we can actually vary the two independently by varying the fluid viscosity, by varying the initial height, and also by varying the speed at which the two plates separate. And here's an example. How am I doing with time? I'm doing actually not bad. Huh? So this is about two different viscosities and two different, there's the same aspect ratio, but we change the capillary number by changing the viscosity of the fluid. Here is a 4 Pascal second fluid, and here's a 48 Pascal second fluid. And let me see if I can play them both at the same time. Oh, yeah. So if this value is large, you have a small number of fingers. And if this value is small, you have a large number of fingers, larger number of fingers. Now we play with the other parameter. We keep the same capillary number by fixing the viscosity and the speed, but we only change the separation height between the first and the second case. And this is what we see. Yep, it's coming. You have small number of fingers, and this value is smaller, then you have a large number of fingers. And again, this is what, if you were an artist, you would want to create something as pretty as this. Okay, so in the case of Remedios Varo, again, the action is controlled by this instability which is driven by the surface tension, the competition between surface tension and viscosity. And again, you can create a wide range of patterns depending on the ability that the painters have to control the initial configuration, the properties of the fluid, and they do this 1,000 times such that they can produce the pattern that they want that is part of their composition. So in this case, you do want the instability, as opposed to Pollock that wanted to prevent the instability and cicadas that wanted the instability to happen, right? So in general conclusions, and again, it's a real privilege to be here in front of you speaking about this exciting subject today. So this comes as a realization that fluid mechanics can actually be useful to something as pretty as art. Again, the connection between the instabilities and pattern formation has been evident. Those of us who attend this fluid mechanics, the division of fluid dynamics, we know that the gallery fluid motion is actually an immense hit, and many of the patterns shown in the gallery fluid motion are the result of hydrodynamic instabilities. So there's no surprise that this is actually a tool that you can use to create these beautiful patterns. And again, you can use it to produce the patterns, or you can actually try to prevent them to create what you want. And again, what has been surprising to me is that there's actually an explosion of interest from the art history and the art appreciation community to learn about fluid mechanics. So these are 4 other projects in which I'm involved that have this fluid mechanical flavor to understanding creation in art. So here's the famous coffee ring instability that people do watercolors. They learn to control or to produce. You have another painting technique used by artists that I call the flying catenaries. They took a brush with paint and then just go like this, and this is what you can produce like this. We actually, I'm afraid to talk about this because I'm in a mathematical institute. You can actually use topology to characterize the amount of complexity in an abstract painting. I can tell you a little bit more about it if you want. And we're actually starting to look at how the properties of the paints, in this particular case wax-based paints, change with colors. For instance, for the same composition, this is very fluid and this is very paste-like. Changing only the type of pigment that you use to create, to give the paint color. It's very exciting, and we understand very little about it. So with that, I thank you for your attention.
Thank you for this beautiful talk. Let's go.
Okay.
Yes.
I'd like to make 2 brief comments and then ask you a question.
Yes.
First comment is, your talk beautifully illustrates, with some extended examples, the book by Philip Ball called Bright Earth, in which he claims that although art historians usually don't emphasize this, every innovative artist throughout history has used the latest materials and technology to produce their work. He studies this in very great, even now with the iPad.
It's correct, yes.
So,
thank you. I will look it up.
is a story.
Yes.
The very excellent physicist Dan Kleppner told me that in the 1950s, when he was in Harvard, and Pollock's paintings had become popular,
Yes.
there was a lot of skepticism about them, and people said, "Oh, this is not art. Any child could do this." And he and some colleagues, fellow students, decided that they would produce Pollock paintings. And one night they got very drunk, they bought some paint, and they found they couldn't do it.
Yes.
So this was the story, so he tells him. Now my question is this. There are papers, at least one anyway, which analyze the fractal dimension of Pollock's paintings. And my question is, can you understand that fluid mechanically?
This is the question you didn't want anyone to ask.
No, it's fine. I had nothing to do with the fractal thing. No, it's fine. Yes, well, the answer is yes. Pollock had certain knowledge about fluid mechanics. That's my hypothesis, right? So it's not, I could not paint like Pollock if you give me a bunch of beers and a bucket of paint, because you need to learn about how to avoid the curling instability, right? And with respect to fractals, I'm one of those who don't believe in this fractal analysis, and that's why we try to use a different.
When you say you don't believe it, that's a private psychological
Yes,
statement
yes.
about yourself.
Yes, that's true. Yeah.
Do you mean that you think that the people who did the analysis of the pictures did it wrong?
No. So if you look at, let me.
Or that you prefer to study other aspects?
No. Let me be more precise,
Yeah.
because we need to be precise in our business, right? Here's one of the paintings that I showed. In my view, not being a specialist in fractals, a fractal is a geometrical image that repeats itself in different scales.
Or statistically.
Yes, of course. But if I take a piece like this, if I scale it up or scale it down, in my view, it does not have significant fractal properties. That's my view.
People measure the fractal
Yes.
dimension. So
They have, yes. But I don't know if it's meaningful or not.
Well, surely if you make an image of a fractal set,
Yes.
it fizzles out after a finite number of layers.
Yes.
Oh, sure.
Therefore, one cannot say of that image that it is not an image of a fractal.
Okay.
But it's not
Fair enough. I'm not a
Not
specialist.
that it is a fractal, but we can use the tool of fractal.
Yeah,
Fractal and fractal.
every fractal
To
has a
pull
finite
numbers
range
out of that.
this.
The same way you can do it to Mozart or Bach.
So again, just to finish with your question, what we have done is we actually flipped the coin and not use fractals, just use the topological invariance, the Batty numbers, to measure holes and connected lines. It's a different aspect, but because of this.
It's what Nando would call lacunarity, at least part of it is.
Yeah, exactly.
One of the
Yeah.
Okay, Stephen?
Thank you.
Jackson Pollock didn't always paint without little wiggles. There is at least one painting that I know of in which you can clearly see little coils and meanders and transitions between coils.
It's in Andre's paper. Yeah, and that's the only one that we could find.
Is there really only one?
No.
Maybe Andre is the specialist.
There are many more.
Yes.
But sometimes the coils are not visible clearly
Yes.
because they are on the woven canvas, which is uneven and which destroys very fine coiling effect.
You have a curling phase.
Yeah.
But isn't it that the dripping itself and instability in the first place? He seems to be using that a lot, right?
So actually, if you use less viscous fluids, then you have another instability, which is the Rayleigh plateau instability, in which the jet would fragment itself and they will paint something else.
Seems to be important.
It could happen, but again, I'm broadly speaking on this particular set of paintings that we're trying to understand. Yes.
Between the straight line in Jackson Pollock and the curling, there's a regime where you get a perfect sinusoid
Yes.
if it's pulled at just the right
Yes.
rate.
Mhm.
It's rather beautiful.
Yes.
And I wondered, did he actually make use of that, Angie?
My guess is not. Again, maybe Andre and I can have a heated discussion about this, but I'm an anti-believer of curling, and Andre has a different opinion.
I've seen it clearly. There's a painting in which it's very clear.
Yes, one painting.
One painting.
Yes, I give you the point. But like, for instance, this Hans Namath filming, which may be influenced by the fact that he was being filmed, in that case, you can see clearly that you have straight lines and not curly lines.
Did he ever say that he was avoiding?
No, of course not. He didn't know.
He just didn't talk about that.
Exactly. Yeah, he was more interested in other things beside painting. He was more into drinking.
Drinking. That's so many.
While Andre is still setting up, we can have more questions. Yes.
You mentioned that Jackson Pollock was meticulous about the fact that he was using very fluid paint.
Yes.
If your final instability, that whatever you call it,
Decalcomania.
decalcomania.
Yes.
Firstly, I have no idea why the word mania is in there. It's very easy to see if you use in particular, if you use thick paint, which has a yield stress, of course. And you said nothing about yield stress in your talk.
No.
It seems to me that when you're applying fluid mechanics to painting, then with a few exceptions like Jackson Pollock, you really have to think about that.
That is correct. Yeah. Most painters use paste-like materials that have yield stress. We have particularly focused on those paints that are very liquid-like.
But with the decalcomania, if you take just thick buttery paint and you can just do it between two plates of glass, lift off the top plate, not only do you get that pattern, it's got this nice kind of mountain range structure.
It'll freeze there. Yeah.
It's completely solid.
Yes, for sure.
It is extremely decorative, actually.
Yes, for sure. Mhm.
And perhaps the best known examples of that are something very closely related with the Rorschach pattern, where you're pulling away a folded sheet of paper and the pseudo-random, because in fact they use a specific set of these swatches to then carry out the microelectric test. A particular set of decalcomania patterns that were used for many years as a ease by which they were judged of minds.
Okay, so we'll have more food for discussion.
Right.
Thank you again, Roberto.